Uh, Great. Let me see if I can start my share. Okay, what am I sharing? That's what I'm trying to make sure. Let's see.
There you go.
All right. I'm going to restart the share. Give me 1 sec.
While you're starting that, I see that Kent has chimed in, and Kent, we're glad to have you here as well. This is Dr. Karama Fridi from the University of Colorado at Boulder, and he'll be presenting on capacitive wireless power transfer. How are you, Kent?
Very good. Thank you.
Good.
So for some reason, it's not letting me select my PowerPoint. Do you see do you see anything?
Yeah, I do see your PowerPoint, and I also,
Okay.
you can just minimize the Zoom Pro account.
Right. Okay. I will just make this full screen, and I think I shared my desktop, so you guys can. Unfortunately, you're probably seeing. Are you just seeing the PowerPoint, or are you also seeing yourselves?
We're seeing the PowerPoint here, and I'm assuming that everybody can also see just a thumbnail of themselves.
Yes.
Very good. I think you're set, ready to go.
Great. All right, I'll get started then. Welcome. Thank you for joining this select brown bag talk on capacitive wireless power transfer systems. I'm going to second. It's not letting me move this without. Let's try this. Okay. All right. So what I'm going to do today is go over a few things. I'll start with a quick review of the different projects that we're working on here at CU Boulder. Then I'll give a brief introduction on wireless power transfer, followed by a more detailed discussion on capacitive wireless power transfer for both stationary and potentially for dynamic charging. And then we'll conclude. I'll try and finish all of this in about 30 minutes, so we have plenty of time for discussions at the end. But feel free to ask questions along the way. That's fine. All right. So here's a snapshot of the different projects that my group is working on here at Colorado. My primary focus is on high frequency power electronics, although I also work in power electronics at traditional frequencies for higher power levels, but more and more the projects tend to be at higher frequencies. In terms of the application domains, there are a couple of projects on electric vehicles. One of them is what I'm going to talk about now, which is the capacitive wireless power transfer for EVs. Just very recently, we concluded a project that was headed by Professor Bob Erickson, and Professor Dragan Maksimovic was part of the team, and I was part of that team, where we developed a drivetrain architecture, and my part of it was focusing on the integrated charger that went with that drivetrain for the electric vehicle. There's lots of projects in the telecom data center space, again, focusing on high power density while maintaining high efficiency, and also maintaining high efficiency when the converters are working over wide operating ranges in terms of input and output voltages and power levels. Another focus of my group is in lighting, again, miniaturization of the power converters associated with LED drivers and for DC applications like automotive, as well as offline, in which you have to take care of energy storage as well, and come up with techniques in which you can extend the life of such drivers, where traditionally you've used electrolytic capacitors for energy storage, or the AC buffering, the twice line frequency energy storage. We have developed some techniques where we actually can utilize film or ceramic capacitors and yet maintain the energy density that you would expect with electrolytic capacitors. There's also some work funded by both industry and NSF on some fundamental techniques. Some of that is targeted towards WPT or wireless power transfer applications as well. And we'll be talking a bit more about this as we go along. All right, let me dive right then into wireless power transfer. And wireless power transfer, although is become popular very recently in the last decade or so, its actually origins go back over 100 years, back to Nikola Tesla. Was when he was doing his experiments with trying to power the entire globe by wireless transmission of power. Some of that work was actually done here in Colorado, the south of where we are, down in Colorado Springs. You can see this photograph here with Tesla sitting in the background, which is actually, he wasn't really sitting there, was that image was created by him, but he did all of those experiments. So we know you can transmit energy across distances through air. Whether you can do it safely or not, and whether you can do it efficiently or not, has really been the challenge. And the technology to actually do this well did not really exist at the time Tesla was doing his stuff. So we now have an opportunity to really push the technology further. And there have been a number of approaches which have been tried or are being worked upon. Inductive is sort of the most well-known, especially for near-field applications where you're talking about distances which would be compatible with electric vehicles. Also, slightly larger distances for charging cell phones and other devices that may be lying on your table at a distance from the actual charging station. And then capacitive has traditionally not been a favored technology, and we'll talk about what were the impediments and how those can be overcome with sort of what is becoming available now. Other technologies include radiative ones, such as electromagnetic beamforming, using either microwaves or using laser. That's more for very specialized type of applications, sort of sending energy to airborne drones, or again, sort of for space applications and things of that sort. There's also some work on using pressure waves or sort of acoustic technology, where you try and focus the energy to a specific area and use ultrasonic sound waves. Again, how practical that is to be determined. But you have all of these different approaches. There's a whole bunch of applications, starting from very small appliances all the way up to larger things. Our focus today is going to be on electric vehicles, but there are a whole host of applications, as you can see on this slide. I'll start by giving a brief introduction of inductive wireless power transfer, just to kind of set the stage and also explain some of the basic concepts, and then move to capacitive. So inductive power transfer at the fundamental level can be thought of essentially a loosely coupled transformer. So you don't have very high coupling, and so you have to, in order to get enough energy across the large air gap, you have to rely on either producing very high voltages, and at the same time you have to rely on trying to compensate for effectively the leakage inductance, where most of your voltage is dropping. And sort of from a power electronics perspective, we think of the transformer as a magnetizing inductance and as a leakage inductance. If you have a loosely coupled transformer, most of your voltage is going to drop across your leakage inductance and not show up across the magnetizing. So the way to kind of overcome that challenge is to resonate out the leakage inductance. And you can do that by putting a series capacitance. And that's one of the techniques people use. You can see that sort of down here in the figure. You can do series capacitances on both primary and secondary side, or you can also do compensation or sort of resonance using parallel capacitance, and obviously you can combine and these in any combinations. You can also use higher order networks, and so there's lots and lots of varieties. In general, I will use the radio frequency community's terminology for these compensation networks, which are called matching networks. And matching networks have traditionally been used in radio frequency applications for providing gain, sometimes also for providing compensation in terms of reactive compensation, but typically it is for impedance matching, for example, in antennas and stuff. So instead of using a transformer, you use a lossless matching network, which just comprises inductors and capacitors. In terms of the standards that exist today for wireless power transfer, in the inductive approach, there's the lower frequency G standard, which is typically for shorter distances. And there is the Resens standard, which is the 6.78 megahertz standard and is being applied for longer range applications. For EVs, there is a separate standard in the works. The SAE J2954 committee has a technical information report out, which has a proposed standard for with frequencies in the 81 to 91 kilohertz range for sort of level 1 and level 2 type of charging. The document is available from SAE for those who would want to learn more about that, but I presume many of you have probably already seen that. Now, there have been a number of inductive WPT systems that have been built. I'm showing you one which was built at Oak Ridge National Lab. They have a version which is for stationary charging, which is shown above. And they've also experimented with dynamic charging with sort of multiple pads which power up in a sequence, and the vehicle goes over and gets charged. Again, in the sort of circuit topology, you can see the same concept of sort of the matching network, except here they're using a transformer, which is a sort of like a broadband matching network, and then they have a compensation capacitor, and then they actually, this is their essentially the coil or the coupling. All right, so that's all great. Now, if you want to extend the concept to dynamic charging, the motivation there really comes from trying to reduce the size of the onboard battery, because batteries tend to be the most expensive or one of the most expensive component of electric vehicles. They also limit your range and sort of add to the time it takes to recharge your vehicle. So if you could charge on the go, that would certainly be a great value addition for customers. The practicality of this is something that needs to be worked out, but there are certainly a lot of experiments in progress to try and sort of see if this can become a viable solution. And I think certainly for certain applications, it makes sense now. And certainly there's a possibility that in the future, this becomes practical where you have an entire charging lane and you have vehicles that move into the charging lane and get charged and then move out. So I'm sure many of you are familiar with that. We'll talk more about this in context of capacitive when we get there. So to kind of introduce the capacitive charging, let me talk a little bit about what are the potential challenges or what are the challenges with inductive wireless power transfer. All of them stem primarily from the fact that you need to focus the fields in an inductive system, and you do that by putting ferrites around the coils themselves. Now, these ferrites impose two constraints. One, they are fragile, so embedding them in the roadway is a tricky prospect. Two, they add weight, and they add weight on the vehicle side as well. They are also expensive, at least they add cost. And secondly, because the ferrites are part of the system, and you have sort of magnetic fields which are AC going through these ferrites, you tend to have losses in those ferrites. And these losses become far more exaggerated once you increase your frequency. So the relationship between frequency and the size of inductive and capacitive systems is well established, and it is a direct impact. So if you can operate at higher frequencies, you can actually reduce the size of your coils and get the same power transfer. But because you have ferrites there, you're limited on how high a frequency you can go to, which is why you see all of these, many of these standards operating down in the tens of kilohertz range. So with that sort of in mind, let me then introduce the capacitive system and say how we can potentially overcome some of these challenges. So by way of introduction, let me say a few words about what's been done in capacitive in the past. Capacitive has been tried for charging things like cell phones, where you can actually put your device right on top of the pad. The problem with capacitive, and it's been sort of what has been quoted in various ways. In fact, capacitive was ruled out for anything like an electric vehicle until recently, is that the capacitance you get between your the appliance that you want to charge and your pad is very small. So it's very hard to get large amount of power across the system. And it certainly becomes much more difficult when the distances increase, because your capacitance just goes down as 1 over the distance. So that was the problem with capacitive. But on the same time, because you're not using any ferrites, because your coupling mechanism doesn't require any coils, and it's just a flat piece of metal, the system can be much less costly. It can be more efficient. And because you don't have, again, ferrites, you can push up the frequency and make it smaller. The size versus frequency relationship holds here as well. So you can, as you can imagine, even though your capacitance doesn't change, or the capacitance may be fixed, your impedance of that capacitive connection goes down as you increase frequency, and so you can get more power through the system. So some of the first early experiments that were done for EV type applications in capacitive systems were done in Japan, where they tried to actually push power through the tires. There are two problems with that. One, tires are fairly dissipative because they have carbon black filler in the tire material. And secondly, the contact area of the tires with the roadway is fairly limited. The approach that these people were trying to take was the fact that the tires tend to be the closest thing to the road, so that minimizes your distance, but the area that you really have available is fairly limited. So the best somebody was able to get was maybe like 50 watts through tires in a small vehicle kind of application. And with efficiencies that were sort of in the regime of 50-60% at best. So our approach is different, and it is to basically go through the air gap. The challenge there, of course, is that you have a large air gap, 12 to 16 centimeters in distance for a typical vehicle. And that means your capacitance is really small. We're talking about capacitances in the order of picofarads. So in order to push any reasonable amount of energy through that capacitive interface, you need to be operating at fairly high frequencies. So that's one constraint, which was one of the limiting factors why capacitive were sort of not promoted about a decade ago or even 5 years ago. The other constraint is that you still have to worry about safety limits, which you also have to do in inductive, where you deal mostly with magnetic field limits. Here you have to deal mostly with electric field limits. The electric field limits actually drop as you go up in frequency, although they do sort of flatten out as you get up to sort of higher frequencies. And eventually, actually, they come back up at high enough frequencies because the electric fields are essentially not penetrating your skin. But anyway, for the frequency that we will be talking about, you're working at about 50 volts per meter kind of electric fields. That's kind of what you're allowed to have. So in order to be able to push large amounts of power through these capacitive interfaces, if you look at the figure on the left, you really need to have your displacement currents, which is effectively how the energy is going through these capacitive interfaces. That displacement current has to be really small. And so in order to get still reasonable power through that interface, you need the voltage that you're applying at that capacitive interface to be fairly large. And you want the voltage that appears across the plates to be small. And that will be small as long as the current going through that is small. So the goal then is to be able to somehow develop stages which can boost up voltage to considerably high voltages, get the displacement currents to be small, so you still get high power, but essentially low voltages appearing across the plates, and which then results in the electric fields. So if the voltages are small, then the electric fields will also be small. Now, one other thing that our approach takes advantage of is that, and I'll show that with this slide. Actually, I'll wait for a second and show it in the next slide. So let's now talk about sort of the constraints that are imposed in the capacitive system. So there are fundamentally two constraints. One is the constraint of air breakdown. The air breakdown constraint is actually quite relaxed. You can get power transfer densities easily in the hundreds of kilowatt per meter square level and not have air breakdown issues. On the other hand, the safety limit, even with sort of going at high frequencies, you get constrained by the safety limits that I just spoke about. These are sort of the ICNIRP standards. And so if you put in the safety constraint, you see that you're really constrained down to power levels or power transfer densities. And power transfer densities is a metric that I'll be using multiple times. So let me just describe that. That's really the power transferred through your system divided by the area occupied by the system. Because you have limited area under the vehicle, you really care about how much area you're using. So that's the metric we will call power transfer density. All right. So the power transfer density that you can achieve with these safety limits in place would be of the order of 5 kilowatts per meter square. So if you want to enhance that, what we'd like to be able to do is figure out a strategy by which we can overcome this limit shown by this red line or the lower line. And our approach for doing that is shown in this next slide, whereby instead of having a single capacitive wireless power transfer system, or a single module as we will call it, we have multiple modules. And these modules have relative phases to one another in such a way that the fields outside of those modules are canceling one another. So you're getting an effective field focusing effect where the fields are essentially within the module, where you don't really have the problem of safety because that's underneath your vehicle. But the fields that are sort of outside of those modules, and especially fields that are getting outside of the vehicle chassis area, those have been subdued by this sort of what we call the near field phased array field focusing concept. So there are essentially two key pieces of technology that need to be developed in order for our system or concept to work. One is this field focusing concept, or field cancellation idea. And the other is the design of these matching networks, which allow you to get a very large voltage gains on the side of the the voltage that you're going to apply to the plates, and so that the voltage across the plates is actually small because you have small displacement current. So let me first talk about the phased array field focusing. And in the phased array field focusing, I'll show you here some early simulation work that we did. So if you have a single module which is transferring certain amount of power, you can see the field levels around it, and the red indicates high fields. And you can see a lot of red. So there's a lot of field at a distance from that module. And that's also indicated, that's also indicated here in this chart, where you can see sort of these fields above safety level. If you break that module up into two modules and you phase them out, phase them by 180 degrees relative to one another, then the fields outside the system actually tend to cancel. You still get the power transfer through the system through appropriate system design, but the fields outside do tend to cancel. And so by, again, taking this further, adding more modules, you can reduce the fields outside and get the same power across the system. All right, now this simulation was done using Maxwell. This is using HFSS, which is so Maxwell does quasi-static analysis. This is full wave dynamic electromagnetic analysis. And again, you see the same results. Between the modules, you see high fields, which basically translates to high power going through. The different lines here are basically associated with different frequencies. But outside in what we call the safety zone, the fields are subdued. And again, the higher the frequency, you have lower impedance, so lower voltages get developed across the plates, and therefore the field levels are lower. But you can certainly see that the fields are being subdued outside through this sort of field focusing concept. We've also experimentally validated that concept. You can see sort of the experimental setup here, and also the simulation setup. And the lines here basically show how the fields are, or the field values as you move away from those modules. The fields obviously naturally decay with distance, but if you don't have the phasing and you're not doing the field focusing, you have higher levels of field. With two modules, with phasing, you can cut the fields down by roughly a factor of 2. And so we've demonstrated that this concept works both in theory as well as in practice. And this is one of the sort of the two innovations that allows us to kind of enable this technology. Now, the rest of the talk, I'm going to talk through on the design of the individual modules, because that's also fairly challenging. And there's some innovations there that I want to quickly go over. I have more slides than I can cover in the next 5 minutes, which is what I'll try and finish up in. But I'll at least show you that. So first, I want to just show you, before we even got this far, but this is about middle of 2015, we were doing some early experiments to see even if capacitive would work. And we built a very simple module, which is only 0.5 centimeter apart. And we used a simple transformer with some sort of L section matching network to get gain. And we demonstrated that at least, yeah, you could get power across even a simple system. And we got like 120 watts of power across a 0.5 centimeter air gap with reasonable efficiency. And we hadn't done a lot of hard work to improve efficiency at that time, because this is just some early prototyping. So it gave us confidence that this is possible, but this is still quite far from the 12 centimeter air gap that we wanted to actually go after. I should say that at the time that we did these experiments, these were record breaking. So the best that had been done at that time was like 2 millimeters or so, or maybe 3 or 4 centimeters, 3 or 4 millimeters. So less than 0.5 centimeter, and powers of under 50 watts. So our results, even though they look very preliminary, were exciting. In order to actually design this single module, what you have to focus on is the matching network. What we had done earlier was essentially use a broadband matching network, which is a transformer. But a transformer is not a great way to use at high frequencies, because you can again have ferrites and losses. So what you would really like to do is use at the high frequencies we're considering using, which are 6.78 megahertz to start with, and then 13.56 and possibly. what you'd like to use is essentially air core or low permeability magnetic materials for your inductors, and and build your matching networks that way. The matching network actually does two things. So one, it provides you gain, which I spoke about much earlier. The other thing it does, it provides the compensation for the reactance that this capacitor is providing, or this capacitor has. Now, if you just put an inductor in series, you'd actually need a fairly large inductor to compensate for the impedance of this capacitor, because the capacitance is so small that its reactive impedance is pretty large. On the other hand, if you are actually using a matching network like this, because you're getting gain, there's an impedance transformation that's occurring, just like as it would in any gain stage, like in a transformer, where the effect of this reactive impedance is essentially suppressed by the square of the gain of this matching network. And so the inductor you need on this side actually is much smaller. And so the matching network will play an important role in providing you both gain and compensation. So I'm going to quickly go over the next few slides because they are highly technical, and I'll come back to them in question and answer as needed. But I want to first talk about what we did to get high gain, high efficiency matching networks. Now, the traditional way of designing high gain matching networks was to not use a single stage, because a single stage will become extremely lossy or be highly inefficient because of the limited quality factor of your inductors. Your capacitors tend to be much higher quality factor, so you're really limited by the quality factor of the inductors. So what you typically do is you split it up into multiple section matching networks, and the traditional approach had figured out what is an optimum number of stages to use for a given amount of gain. That optimization and that sort of well-established method of designing matching networks imposed one constraint, which was that you assumed that your final impedance, which is typically a resistive impedance, it was also translated to a resistive impedance at each intermediate step of the matching network. So all of these matching network stages were designed with resistive input impedance in mind. And that conventional design approach then basically came up with an optimum which said that in order to maximize efficiency, you need to split gain equally across all of these different stages, which kind of made sense. You're basically stressing each stage by the same amount, and that would essentially give you the optimum efficiency across your overall cascaded system. We asked the question, what if you didn't impose this resistive constraint at the input of the intermediate stages? Because for a matching network, you're starting, let's say maybe you're loading it with a rectifier, which looks at fundamental frequency as a resistive load, and you're looking, you have an inverter, and for the inverter to have zero voltage switching and near zero current switching, you need it to be slightly inductively loaded, but fairly close to being looking resistive. So what if, but for the intermediate stages, you don't really need that constraint. So how about we relax that constraint and see if that gives us a benefit? So in what follows is the math to kind of work this out analytically. And so what we did was we established a nomenclature for how to do this optimization, where we've now established a output impedance and an input impedance, which is not purely resistive for each stage. And then we establish a way to quantify the efficiency of a multi-stage network. And then we use a Lagrange multiplier. So this is the multi-stage efficiency. We use a Lagrange multiplier approach to then figure out the optimum. And when you do that math, which is actually fairly algebraically complex, you come to a very interesting solution. It turns out that there is an optimum. The optimum actually tells you two things. One, it tells you that the optimum is not where all the gains are equal for all the stages, which is different from what was in the standard design approach. The second thing is you actually want the input impedance of each of your n-1 stages, where n is the last stage, so the stages before that, the input impedance of those stages to be equal to the negative of, the input impedance of all your stages, starting from the second stage to the last stage, to be equal to the negative of the gain of the previous stage. That's a very surprising, non-intuitive result, but it is the result that gives you the maximum efficiency. So, so clearly, this relaxation of constraint allows you to have more efficient systems, and it predicts for a two-stage network efficiency gains where you can reduce losses by up to 20+%, three-stage networks where you can reduce losses up to almost 35%. And the actual efficiency depends on the quality factor of the inductor, although the reduction in loss is independent of the quality factor of your inductor. So here again, you can see for the two-stage and the three-stage design, sort of the conventional approach and the improved approach, how the efficiency differs. And then we also validated this through experiment, and we saw exactly what we expected. We got a loss reduction of about 25% in a three-stage, in this particular three-stage design, and running at 1 megahertz. Now, this so far was just providing gain. So it hasn't provided the compensation that we need for our capacitive system. So we extend now this to the capacitive system, where we also need, so we have a voltage gain stage, but this voltage gain stage, in addition to providing voltage gain, also needs to provide compensation. And the question is, how much compensation should you provide from each of the stages? You could provide it all by the first stage, distributed equally, or provided by the last stage or some other stage, or some combination thereof. And similarly, you could split that compensation between the voltage gain stage or the current gain stage. So whether it's on the primary side or the secondary side, and all of that, you need to figure out what's the optimum. So we extend the same kind of math now to also provide compensation, and we set up the same problem. We go through all of that, and we come to results which are again very revealing. First of all, it says that for the gain, you actually provide gain exactly the same way as we did in the previous case, which actually is that the first n minus m, so we have m stages, so you provide equal gain from all but the last stage. The last stage actually provides a different gain, and then in the reverse order, the first stage provides different gain from all the other n-1 stages. However, the compensation you want to equally split across all those stages, right? And that turns out to be the optimum in this case. All right. So now that we have established the two sort of fundamental principles, let's go back to the design of our system and start to ask, what is it that we would be able to do? This slide here just kind of validates our math. So we had an analytical way of predicting the efficiency and the optimal efficiency. We've also validated that by doing exhaustive numerical search over all the possible designs. And as you can see here, the solid lines show our analytical results, and the dots show the numerical optimization results. And they match very well. The reason they differ at lower quality factors of the inductors is that in the analytical analysis, because of the math being fairly complex, we made the approximation that the quality factor of the inductor is large. And under that approximation, the math becomes a little relatively simpler. And so that's where you see the very good match between the analytical and the numerical. Now, for realistic systems, the quality factor is going to be around 200. So, and you can see there's a fairly good match. So with that all done, here's what we predicted as what is possible with our system. So we can for a system where we achieve 50 kilowatts per meter square of power transfer density, we predicted we could get efficiencies above 90%. Right? So you can kind of, there's a sort of a simulated system. This is not built yet. Right? Now let me kind of go and tell you what we've built so far. So one other thing I should say is, so far I showed you circuits which looked like these at the top, where we have this L section matching network on the primary side and on the secondary side. When you actually start to build them in practice, you want to split up these inductors across both the forward path and the return path for two reasons. One is by making the circuit symmetric, you get rid of many common mode issues. Also, by splitting the inductor, you need to build inductors which are half the size, so that or half the inductance. And as you will see, one of the major problems with capacitive systems is being able to realize inductors which have high performance at the frequencies that we're talking about. And one of the major challenges there is to be able to build inductors with high quality factor and have high self-resonant frequencies, so that they actually act like inductors and efficient inductors at the frequencies we want to operate them at. So now I'm going to just briefly tell you results. As you will notice that at the bottom of slides, it also says confidential, and I request that you keep the information I'm not presenting confidential because it's unpublished. Hopefully in a few months, this will all be published, and we will be able to sort of share more broadly. We've built a number of systems. This is one of them. This is a 12 centimeter system with a plate dimension of 17.7 centimeters by 17.7 centimeters, operating at 6.78 megahertz. This has an air gap of 12 centimeters. And we have a operating frequency of 6.78 megahertz. We get 190 watts of power transfer through the system, which corresponds to power transfer density of 3 kilowatts per meter square, and we get an efficiency of 90%. All right. This is essentially using a single stage matching network, which is where we wanted to start with. Since these are highly tuned networks, we wanted to make sure that we knew how to build good single stage matching networks and systems using them before we started going to higher order networks. The second one we built is a higher power transfer density system. So that same air gap, 12 centimeters, but smaller plate size, 12.25 centimeters by 12.25 centimeters, and same frequency, but 540 watts of power transfer, corresponding to 6 times higher power transfer density of 18 kilowatts per meter square. The efficiency is lower, it's at 75%. So these are some of our results from work in the last few months. Let me now talk about how do we get higher efficiencies for systems with high power transfer densities. So but before I do that, let me just also show sort of our work relative to other work in this area. There are two groups that have worked in this area in the last few years. One is Chris Mee's group, which did most of this research when he was at Michigan, and Dan Ledoy's work at Wisconsin. And the power transfer densities they have demonstrated are sort of in the 3 to 5 kilowatts per meter square. So our highest performing power transfer density system at 12 centimeters is at 18 kilowatts per meter square. So it's roughly 3 times higher power transfer density. Or actually, not 3, I meant 6 times higher power transfer density. The current performance frontier we have from the two systems it looks like this. So it again goes up to efficiencies of 90% at 3 kilowatts per meter square and efficiencies of 75% at 18 kilowatts per meter square. And now let me just mention how do we get to higher efficiencies from these power transfer densities. So one approach would be to build better inductors. So right now our inductors have quality factors of around 200. And the theoretical efficiency of the system And this is actually the efficiency of just the matching network would be as shown by the solid line, while our experimental efficiency, including the efficiency or the losses in the inverters and the rest of the system, are very close to that theoretical efficiency. So we know that our theory is matching our actual experimental measurements. So if we can build inductors with higher Q factors, we can push our efficiencies up to closer to 90%. That's one way to go. The other way to go is if we have the same inductors, so we don't improve the quality factor of the inductors, but rather go to two-stage networks, then the theoretical efficiency automatically goes up close to 90%, and that would also push us up to close to 90% efficiency. So those are the directions we are taking. In fact, we're taking both directions simultaneously to kind of see how what is the best approach. And so that's essentially the meat of my talk. I'll just kind of conclude with this summary slide, which is that while capacitive WPT systems were previously thought were not really the way to go for large air gap energy wireless power transfer, we have demonstrated that it is possible to get very high power transfer densities through these large air gap capacitive systems. And our approach has really relied on developing very high efficiency matching networks, which enable this to occur, and utilizing a multi-modular approach in which we have multiple modules which are field canceling. The multi-modular approach is also compatible with going to high frequencies, because then each module can be of the level of 500 watts to a kilowatt, or maybe a couple of kilowatts, and you don't have to build 30 kilowatt or 20 kilowatt systems as a single module, which is kind of in line with the GaN technology that's available. I didn't mention, but all of this is using gallium nitride transistors. Some of our sort of results are shown here, and our targets are also re-emphasized. We're still shooting for 50 kilowatts per meter square. By the way, I should say that once we hit 25 kilowatts per meter square with 6.78, we get an immediate factor of 2 theoretically improvement if we just switch to 13.56 megahertz. So our intermediate goal is to get to 90% efficiency with 25 kilowatts per meter square at 6.78 megahertz, and then start moving to 13.56 megahertz systems to get to the 50 kilowatt meter square power transfer density and high efficiencies. So that's it. And hopefully, if all this works out, you want to go dynamic, you don't have to embed ferrites in the roadway. Instead, you just put metal plates, which would be a lot simpler to do. And that would enable dynamic charging as well. And I will just acknowledge my students, my collaborator, Professor Zoya Popovic, and my sponsors are ARPA-E and NSF. We have a bunch of papers in this area. We have a few more that are submitted but not published yet or not accepted yet. So that's why the information is not in print yet. And we got one of our papers actually won this award at the Best Paper Award at Compel. I'll just stop here. You take questions.
Excellent, Karam. Thank you. Thank you very much. Excellent. Very well presented. A lot of information packed in there. We have roughly 10 minutes for some Q&A. I just want to let a few people who joined in a little bit late that we're recording, just so that you're aware of that, and we'll publish this on our website after Karam has had a chance to publish his findings. I will unmute everybody now. You certainly have the option to mute yourselves again if you'd like to, but let's take about 10 minutes to do some Q&A, and then we can also do some connecting with Karam afterwards if need be in other ways.
It doesn't show anything to us. So you have to literally go in and be like, are these approved? Are you like purchasing these on the black market? Like, who are you? So for Brett Hooper, they just left off drive.
Yeah.
I'm going to go ahead and mute everybody again. Okay. I'll tell you what, if you have a question, if you can't unmute yourself, just send it to me via chat. I don't know who was on that. I'll try to find, but go ahead and ask any questions. Prabhakar, are you typing there?
No, I'm just trying to unmute myself.
Okay, it looks like you found it.
Yeah, this is Prabhakar. I guess a couple of quick questions. What happens to that air breakdown limit as you get more humidity in the air? Does it come down anywhere near the levels at which you will be transmitting power?
So that's a good question. We have not looked at all environmental factors of the system. We would like to look at those things and see the air breakdown. Although I should say, if I go back to that chart, we are well away from the air breakdown when we get to 50 kilowatts. So I would suspect that the breakdown of air is affected by factors such as pollutants and water and things of that sort.
Yeah.
But at 6.78, the air breakdown is at about 300 kilowatts per meter square. So we are about a factor of 6 below. So unless it degrades by that much, we should be okay.
Okay. And it's the second last question is the efficiency or the losses, are they on the station one side or the other or both? When you get to 90%, let's say the 10% loss would be split equally on the receiver and the sender side, or?
So that's a design choice that you make. It depends on it depends on two things. It depends on the voltage on the secondary side, because that determines how much of a step down you need from the secondary side matching network. So if you have a high voltage, your matching network requirements on the secondary side go down considerably. So you need much simpler circuitry on the secondary side, and your losses will also go down. But you can decide to split it either way. You can kind of put you can put more losses on one side or the other. Either way.
Where I was coming at was obviously it would require thermal management. You had significant losses on the vehicle side that might be better to design so that you can reduce the amount of loss.
Yes, I agree. You'd also, from just a weight perspective, want to sort of shift all of the stresses on to the primary side as much as possible.
Okay. Thank you. Very good.
Thanks.
This is Lawrence. Can you hear me?
Yes, I can.
Okay, thank you. Very good, Karam. Looking forward to our getting together in April. The question I have is the rate at which you can transfer the energy leads itself to how do you capture the ability to send such a massive amount of energy across in a very short space of time. And chemical batteries themselves have got a limit to how fast you can charge them.
Right. And
have you looked into some sort of intermediary capacitive storage in order to feed electrochemical battery, or alternatively that the capacitive storage becomes the focal point of vehicle storage?
Right. Excellent question. So the answer is yes, not in the context of this particular project and program, but is under a separate piece of work that we did as a preliminary work. We actually, myself and Professor Dragan Maksimovic actually came up with a concept whereby we can combine different technologies of energy storage, one optimized for power, another optimized for energy, and couple them in a way that has traditionally not been done. The traditional way has a problem that you need a lot of power electronics interfacing. So we have a methodology by which you can eliminate much of the power electronics in that interface and have two separate technologies be deployed on the vehicle side, one for basically absorbing large pulses of power and the other one for energy. I am happy to talk to you offline about that if it's of interest.
Definitely of interest. This is a pretty radical move. So yeah, that's all part of my interest. Thank you.
Okay, wonderful.
Any others in the last couple minutes here?
This is Lawrence again then. Obviously, if we're going to put something down on a road, which is going to be run over, then, sort of we need to, sort of understand the ability to make a durable plate framework, and certainly much better than trying to bury an inductor in a roadway. But have you given any thought to the materials associated with something that's going to be under high stress?
So we're currently using air core inductors in all of our designs. So the advantage there is that they don't have as many different materials involved, so you don't have to worry about thermal expansion and contraction, just heats thermal cycling kind of issues. One of the things we are, however, looking at, so at this point, what we're doing is we're writing a phase 2 application for our ARPA-E project, where we want to take the technology we've developed and make it vehicle compatible, meaning make it more like it becomes closer to a product. And so as part of that effort, we're actually listing tasks that would do what you just said, which is look at what we need to do in terms of packaging, in terms of different materials that can be utilized for roadside as well as vehicle side application.
Okay, thank you.
I have one question. It's Conny here. Do you hear me?
Yes, yes.
Yeah. My question is here, when you have reached the target 50 kilowatt per square meter, and you put a plate in a car that is acceptable for the car manufacturers. Mm-hmm. I mean, they strive for very small coils, for example, when we talk about inductive. What amount of power can you really transfer then over 12 centimeter air gap?
Right. So you can do that calculation very quickly. So let's assume we are able to hit the 50 kilowatts per meter square target. Then that basically means that if you are allowed 1 meter square of area underneath the vehicle, you can do 50 kilowatts.
Yeah. And that's on the border what you can packaging in the car, but the level is quite good enough. I mean, 20 kilowatt, if you can reach that, then it's a very good target for both dynamic and really some kind of semi-fast charging if you reach that target.
Right, and that's the target we're sort of aiming for. And we're at 18, so we're not orders of magnitude away. We're sort of a factor of 3 away.
Yeah, and the concept is light because you don't need any ferrets.
That's right.
What is the tricky thing? Is that the environmental factors, or what kind of problem can you come into? So
those are the things we want to study in our phase 2. We have not looked at environmental factors yet. We would love to also kind of do some of these studies in partnership with some of your companies if you're interested, because some of you may have more experience on sort of the challenges vehicles have to go through. So be happy to talk to whoever may be interested.
Well, I'm gonna stop it right there. I'll let you two. We'll hook you two up, and Karam and Lawrence as well. Our time is spent. Anybody who wants me to connect you with Karam, I would be happy to do an email introduction. You can also look him up. He's easy to find. He's very well credentialed and well known. Thank you for joining us for the Select Brown Bag today. And we plan on seeing you for next month's as well, and we'll get information out on that very soon. Have a wonderful day. Karam, thank you again. Great presentation.
Thank you. Great session.
You.